We can start with some discussion. Probably did you had a time to look at the paper, this the effect of data encoding in the expression of variational quantum machine learning models. Anyone has any major doubt, comments, complaints? No? So that means everyone got everything completely right? No? Okay. So I'll tell you what I do. I'll look at the paper. Let me look at it and maybe do some notes. Okay, I assume that can you all see my screen?
Yeah.
Yeah. Okay, good. Yes. So, uh, so I know not anyone is aware of this thing, Fourier type things. So I'm gonna skip that. I'm gonna use it as a black box, and I'm gonna tell you what it means. Then, okay, but I want to look at this thing. So the quantum model as partial Fourier series. So again, let's ignore Fourier series for now. And let's look at this paragraph there. We define a univariate quantum model, f theta x, as the expectation value of some observable with respect to a state prepared via a parameterized quantum circuit. This thing here is an expectation value. Let me try to make some notes here of what it means. So this f theta of x is this huge symbol. So it says u dag x theta. Then there's an m, and there's the same u, but without the dag. Uh, Sorry, I'm trying to write with my mouse. Okay, u x theta, and then there's another 0 there. Okay, from here I'm going to tell you what this means. So first, ignore everything and just look at this part there. The u theta x, what it means is you have a quantum circuit. So let's say like this, and then you have a gate there that controls everything. So it receives the input and some trainable parameters. And okay, and it outputs a state at the end. But it starts with this part here. This part means the initial state. In this case, what you do is every qubit starts on the state 0, like this. And sometimes we denote this by 0 dot 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 0 ket, or 0 and then a tensor power there, and then n, where n is the number of qubits. Yeah, so this part, what it means is you apply this u x theta on the 0 state. So what it means is this u x theta, it's a quantum circuit like this that depends on the input data, this x, and on some trainable parameters, the theta. After that, you end up with a state that we can call psi. Now, this psi depends on the input data, x, and the parameters theta. What I'm going to do is rewrite this thing because, no, actually, I'm going to tell you the definition of the other thing. So if I write it down like this, x theta, this symbol means, So I'm going to define this symbol as doing psi x theta get DAC. Now here the DAC, this symbol there, what it means is transpose and then you do conjugate. Because the psi x theta on a ket, so just this part here, this part here, it's a vector. It's a complex vector. And it's a column vector, so it's something like this. And it has some complex numbers, Cn. So the DAG, what it means is you transpose this. Now it's a vector. Instead of being a column vector, now it's a row vector. And each one of this, so this C1, let's say, is equal to A1 plus I, where I is the square root of -1, B1. And I'm going to denote C1 bar. This is just changing the sign. So it's A1 minus I B1. And here, so I did the transpose. Now this column vector is a row vector, and each element is going to be replaced by the transpose, so by the conjugate. So C1 bar all the way to Cn bar. Okay, good. Now, what we do with this, what it actually means is that we have a state that we prepared with this quantum circuit, which is this ket of psi x theta. And look at the last part here. This part here. What it is this ket at the bottom. So I'm going to replace it here, but also look at the other part. So this part here, what it means is the complex conjugate of the other part. What it means is what you have is psi of x theta, then m, and then psi x theta. Okay. Then okay. Then how this works practically is we have a circuit, and then after applying the circuit, we do measurements. So we denote the measurements like this. For us, the measurement is always with respect to a specific observable. In this case, M is the C poly operator tensor with itself n times. Now, this is technical, but what it means is you just do the measurement as I always told you. So this means you will get either zeros or ones for each qubit. And in order to evaluate the expected value, what we do is the following. So we sum over the lambdas, and lambdas are either ones or minus ones. So let's say if your measurement outcome is 0, you replace that by 1. If your measurement outcome is 1, you replace that by -1. So this is the value that you obtain after the measurement, and this is the lambda. And I'm going to do a explicit example. Let me just write down the formula. So you sum over the possible lambdas, and then you look at the probability of measuring lambda, now replaced with the value, on the state that you prepared. In this case is psi of x theta. With the quantum computer, we approximate the probabilities. Because what we do is we approximate, we run the circuit several times, and then we average over all the possible values that we obtain, and that gives us an approximation of this probability. These lambdas, we know exactly what it is because we are always taking m to be this C tensor n. And so let's make this more explicit now. I'm going to start with the 1 qubit example. Let's say I have a qubit that starts on the state 0. Then I apply a Hadamard gate after that. Now we know that after the Hadamard gate, we have 1 over square root of 2, 0 plus 1. And then we measure. Now, we know this expression by theory. In practice, we don't know it. We only have access to the probabilities. When we use a real quantum computer, we only have access to the probabilities. What it means is that the state that we prepare here, this psi, it's unknown, but we know this observable. We approximate the probabilities given the expected value, because in the quantum computer, we don't need to know this psi x theta. We only need to know the probabilities to compute the expected value. Okay. Now, what do we do with this? Okay, so we don't know the state. And what we do is we run this circuit and we measure what can we obtain. Let's say 0. Then we obtain 1, then 1, then 0, then 1, then 0, then 0 again. And we run it like 1, 2, 3, 4, 5, 6, 7 times. Now we replace this by the values. I think I told you this, but let me repeat it. So when you have the C operator, when you applied it on the 0 state, you get the 0 state. And when you apply it on the 1 state, you have minus 1. The rule is you look at the measurement outcomes, these zeros and ones, and you replace it by the eigenvalue. The eigenvalue is the number that lies next to this ket. In this case, we have a 1 here and a minus 1 on the 1 state. Okay. Now, if we look at the first one, this 0 means we're looking at this state 0. Now, we replace it by a 1 because we obtain a 0. That means we put here a 1. For the next one, this means we're on the other case. We obtain a 1, so we replace it by a minus 1. And we do the same for the others. Now, this is the lambda. Then we need to apply this sum. How do we do it? So now the expectation value, in this case, of the prepared state. So at this point in time, we have a psi.
Marco?
Yes.
Your last 2 lambdas should be 1s.
Yes, you're right. See, it's not that simple. 1, 1. Yes. Thank you. Okay, then what do? I want to compute this psi on C. And just to rewrite it as before, this is equal to 0, and then the gate that I'm applying. So in this case, this U is H. So I have H dagger because it's on the left. So it means we apply this complex conjugate, and then the observable C, then H, and then 0. Okay? So this is the first expression that they throw to us as if we would understand it, but what it means is exactly this. Now, how do I compute this? I need to do this sum. Cool. So I need the probabilities of measuring this. Now, I don't have access to the actual state, so that means I don't know the probabilities of measuring this thing. What I need to do is approximate the probabilities with these values that I measure from the quantum computer. Okay, so what's the probability of getting the state 0? So the probability of getting the state 0, so that means the lambda is 1. So getting lambda equal to 1 on this psi, sorry, of psi is how many times did I got it? So lambda equal to 1 is 1, 2, 3, 4 of a total of 1, 2, 3, 4, 5, 6, 7. Okay, so that's the probability. Now I need to sum over all the lambdas. Now here I only have two lambdas, 1 and minus 1. This corresponds to lambda equal to 1. So that means in the sum, I need to place 4 over 7. Good. Now what about the other? The other is the probability of lambda being equal to minus 1 on this state psi. And it's the same recipe. How many times did I get minus 1? 1, 2, 3 out of 7. But look, here it means you need to multiply by lambda. So I need to put minus 1 here. So minus, and then the probability, 3 over 7. And this is 1 over 7. Okay, so this is the value we obtain after applying this several times. Now we know how to evaluate these things. Let me just do a 2-qubit example. So let's say we start with the 0 and then a 0. Then we apply some gates. I don't know. I'm going to put it like this. So this is going to be a gate U that we don't know what it is. We don't know what it does, but we know that we can measure it at the end. And so this is an open question. I'll wait for someone to answer me. What are the possible answers from measuring 2 qubits? No one?
Two
Yes.
possibilities. Like it could be a 0, 0 or a 1, 1.
What else? So if you have 2 qubits and they're on some quantum state, all the possible outcomes are 0, 0. So both qubits measured on the state 0. You can have one qubit in state 0, the other one in state 1, then the other way around, and then 1, 1. Okay? Because after measurement, we can only obtain zeros or ones. And this is for each one of the qubits. So that means this is all the possibilities that we can have after measuring 2 qubits. In this case, we have 2 qubits. So that means our observable is C to the tensor 2. We can write this as C tensor C. And we will follow the same recipe. So let's say we obtain these values and then again 1, 1, and then 1, 0, and then 0, 0, and then 0, 0 again, and then 0, 0 again. So let's say we run this and we obtain these measurement outcomes. How do we compute this expected value? We have C tensor C. Okay, now what's the probability? Oh yeah, I need to tell you something else. This, how can I put it? Okay. So what we're trying to do is approximate, again, the probabilities of measuring each one of them. But now it gets confusing because we have more lambdas, right? And we have more states that we can measure. With one qubit, it's pretty simple because we just replace it like this. But what we need to do is multiply the lambdas. Okay, so what we do is we do it in 2 steps. So these are the lambdas. And I'm going to move this thing. Oops. There. Okay. So I have the lambdas, and then we multiply. Okay, and we follow the same recipe. So for the lambdas, for each one of the qubits, we replace the 0 by a 1 and the other 0 by a 1. In this case, in the next one, the first 0 corresponds to a 1, the 1 corresponds to a -1. In this case, we have a -1 and then a 1. Then we have -1, -1. Then -1, -1. Then -1, 1. Then just once, 1, 1, 1, 1, 1, 1. And now we multiply for each one of the results. In this case, we have a 1, then -1, -1, 1, 1, -1, 1, 1, 1. Okay, now we need to compute this thing. This thing right here. The way to do it is we need to look at each different outcome, because we need to compute the probabilities of getting each one of the outcomes. And we do it like this. So now the probability of measuring the state 0, 0 in this case on the state that we prepared, this psi, is how many times did I get the 0, 0? It's 1, 2, 3, 4 out of 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the probability of measuring the state 0, 1. I'm not gonna write the psi now. So out of 9, how many times did I get this one? 0, 1, only 1. Now the probability of measuring 1, 0 is something over 9. So it's 1, 2 times. And the probability of measuring the 1, 1 is what? 2 out of 9. Okay. Now, this expected value, we decompose it as a sum over all the possible measurement outcomes. Now, so that corresponds to the different lambdas that we can obtain. Okay, so the first part is this probability of measuring the state 0, 0. What corresponds to the state 0, 0 in terms of the lambda is this 1, 1 state, and we multiply it and obtain a 1. So that means that for the first term, lambda is equal to 1, and we put this 4 over 9. For the next one, let's say we move to this one. So 0, 1, the probability is 1 over 9. And the value that corresponds to 0, 1, it's, so in this case, So again, we replace the 0 by a 1, the 1 by a -1, and then we multiply the lambdas, and that gives us -1. That means here I'm going to put minus, and then the probability, 1/9. Then the next one, let's say we use 1, 0. For 1, 0, we're in this case, again, the multiplication of these two gives us -1. So we have a minus, and then 2/9. Finally, with the 1, 1, we have a 2/9. For the 1, 1 state, each one gets replaced by a -1. We multiply that. That gives us 1. So that means that the sign is a plus sign. And then we do 2/9. And now this should be like, I don't know, 1/3, I guess. And this is the expectation value. For more qubits, we will have more measurement outcomes, and the recipe is exactly the same.
So Marco, can I ask a question, please?
Yes, sure.
Yeah, is this 1/3 unique for this? Is actually the unique for this combination, or another combination can give 1/3 as well?
Well, actually, let's say in this case we decided to measure 9 times. If I measure again, then I can obtain, let's say, 1, 1. So that adds another factor, and this value will change. So actually, yeah, okay, good question, because in theory, this value can be computed exactly. But in practice, so as they say, in theory, practice is easy, but in practice, it's not. So this is not going to give you the exact value. What we do is we approximate this thing. So this psi with some observable psi gets approximated by this sum over lambdas and the probabilities of getting each one of the lambdas on this psi. And in principle, the probabilities, when you add more samples here, you get closer and closer to the actual probabilities.
I see. Thank you. Thanks.
Yes. More questions, Samuel?
Yeah, I maybe I missed something. I still don't understand the function z, the operator z. Why do you need z here? Could you use something else?
You could. Yes.
Because,
so
let's say if I use identity instead of z equals identity operator, what will be the outcome?
Yes. Okay. Let's do that example. So we need to do exactly the same thing. You just need to know the matrix that you want to measure. In this case, the C is the matrix that has 1 and -1 on the diagonal. So we know the eigenvalues. Let's say you try to measure the identity. So in this case, you have something like this.
Okay.
And so the eigenvalues, they're all equal to 1. If you measure this, then let's say we want to measure this psi on the identity for just 1 qubit. What do we have? So now let's say I measured my qubit and it's 0, 1, 0, 1. And I measure the identity. Now I need to replace this. So this is the values after the measurement. Then I need to replace it by the eigenvalues of I. What do I do? So I on the 0 state gives you the 0 state. I on the 1 state gives you the 1 state. And the value that is next to each one of these, which is the eigenvalue, is always equal to 1. Right? Now, the probabilities of getting each one of them is 1/2. But let's say I add another one just to make it interesting. Let's say I measure 0 after that. Okay, now for the 0, what do I get? So the 0, I need to replace it by 1.
1, okay.
And 1, how do I replace it?
1.
1, exactly. So there's no distinction between measuring 0 and 1 if you measure the identity. You see that? Now, when you compute the probabilities, what's the probability of measuring 0 here? It's 3/5 with a sign of 1. Now, the probability of measuring 1 is 2/5 with the sign of 1.
Okay, so
And this
one.
gives you 1.
Okay.
Yeah. So every time you measure the identity, it doesn't matter the state that you have. You always get this thing equal to 1.
So when you say,
yeah,
when you're saying we are measuring the expected value, this is the expected value of what exactly?
is the expected value of an operator, like the C or the identity, on a quantum state.
Okay, so this is the expected value of the Z operator that we are computing.
Yes.
But
now there are other operators that you can measure. Yeah.
But what's the because we have another operator just before you mentioned the U operator, just in your diagram just below. What's
this U?
Yeah, is it?
This is just a quantum circuit.
Yeah, so is it the expected value of the U operator or the Z operator?
No, here what you have is, okay, maybe I need to write this. So in the quantum computer, you have a 2-qubit system. Then you apply some gates, this U. What this does is it applies some operations on your qubits.
Right.
After this, we obtain a quantum state of 2 qubits that we label psi.
Yes.
Now this psi is written as applying the U operator on the initial state. So in this case, is the 0, 0 state.
Okay.
Now, when we write down the expected value, so let's say I write it down like this. So I was writing this with the C operator 2 times. Now, this can also be rewritten like this. So I have the 0, 0 state, and then U dagger, and then the CC.
Okay.
Yeah, it can be confusing. And then U, and then psi. Sorry, the 0, 0 state. Now, listen, I could do something like this. And then I'm going to put here, I don't know, 8. And it seems like I'm measuring the state A on the 0, 0 state. Okay, so it depends on how you interpret it, how you're able to compute this thing. Now, one restriction that we have is the quantum computer can only measure the C operator.
Okay.
Okay, so that means after the measurement, we only obtain zeros or ones, and we need to replace that by ones and minus ones. We can measure with respect to other observables. So we have the Y and we have the X operator. I don't remember the formula for the Y, but the X is 0, 1, 1, 0. And what you need to do is you need to compute the eigenvalues of this. And it's easy to get them from this expression. So remember, when we apply the X operator on the one state, we change it for 1. And when we apply it on the one state, we change it for a 0. For the Y observable is another thing, but basically what we need to do is we need to convert this X to a diagonal operator, because in this case we don't have an eigenvalue for the 0.
Okay.
Okay, and we can do that with the Hadamard gate. I think the C operator, it's is it? It's H X H. And then you can do something extra on the circuit to change the basis and then rotate your qubit and then measure in another angle. Sorry, in another direction, but this can get technical. So let's start with just the C operator. So yeah, the quantum computer can only measure on the C state, on the C observable, and we can do things to measure in other kind of observables, but it gets more complicated. Does that answer the question, or did I manage to confuse you even more?
No, it's clear. What I was, if I look at your example below, you're showing, so you have 2 qubits, but
Yeah.
in fact, you can differentiate only when between two, let's say when the 2 qubits are in the same state, 0, 0 or 1, 1.
Yes.
You get always a 1. So if the qubits are in the same state, let's say, you get a 1. And if they are in a different state, you get a -1.
Yes.
But you won't be able to differentiate between 0, 0 and 1, 1 because they
Yes.
get the same Eigen value. So does it mean you are sampling just as a subset of the possible probabilities in that circuit?
Yeah, but the thing with the expected value is that it can help you detect. Okay, let me do another example. It can help you detect quantum phenomenon, things like superposition or entanglement. Let me do an example here. If I start with a qubit on the state 0 and I apply a Hadamard gate, then we know that we can obtain 0 and 1 50% of the times. So in this case, the expected value on the state, again, after this, I have psi, and the psi, what it means is applying the H matrix to this 0 ket. I'm gonna put it like this, psi, and then I measure the C, and then psi. Let's say I approximate the probabilities to be almost 0.5. So this will be 0.5 for the value 1, 0.5, and the other one will be 0.5. This gives me exactly 0.
Mm-hmm.
What if I get the 0 state and then I measure it? The possible outcome here is only the 0 state. Now the 0 state, I replace it. So let's say I measure it, I get 3 times the 0, and I replace it by a 1, right? So this is the eigenvalue for the C. This is the lambda for the C. And what do I get now? So the probability of getting the state 0 is equal to 1 because I get it all the time. And the probability for getting the other state is completely 0. So that means the expected value in this case, it's 1. What if I get the 1 state and then I measure it? Then I get only 1, 1, 1. I replace it by -1s. So what will be the expected value in this case? Is the average of all the possible outcomes in this case. So this will be -1. So as you can see, this expected value goes from -1, this is the minimum, up to 1, this is the maximum. But if you're on the extremes, if you're in 1 or -1, that means your quantum state is really not quantum. It's not in superposition. It's either 0 or 1. Mm-hmm. But if you have a superposition, which is a purely quantum property, then this thing is 0.
Okay.
Okay, so it helps you detect quantumness of your state. Other thing that you can measure is the entanglement. Let's say I have 2 qubits that start on the state 0. Then I apply a Hadamard gate, and then I apply C0. This gives us the 1 over square root of 2, 0, 0 state, plus the 1, 1 state. And what this means is that after the measurement, I can only obtain 0, 0 or 1, 1. Let's say I measure 0, 0, then 1, 1, then 0, 0, then 1, 1, and then 1, 1 again. How do I compute the expected value in this case? So I get psi. Now I have 2 qubits, so I'm not going to put the tensor product anymore. So I have something like this. How many times do I get the 0 state? It's 2 times, so I get, this is like 2 over, what is this? 2 over 5. And the sign for this one, as you said, so this depends on the parity of the measurements that you have. So you have 0, 0, that you replace that by -1, or 1, 1. I think it's 1, 1. Yeah. And then the -1 corresponds to the other one. So every time when you multiply this gives you 1 all the time. Okay, now you do this, and then you end up with, so you have 2/5 for the 0, 0 state, and then you have 3/5 for the 1, 1 state, and you have the same eigenvalue. So you get 1. What happens with the other entangled states? Actually, let me put a non-entangled state. So let's say you have the 0, 0 state, and then you measure it. This gives you only zeros. You replace this, and it gives you only ones. What will give you the expected value? It gives you the same thing, right? But if I have another state, like we have another Bell state, like this, then that means I can measure 0, 1 and 1, 0. And when I get the values, I get -1 here, and -1 here, and -1 here. Right? Because the 1 corresponds to a -1, and the 0 corresponds to a 1. I multiply that and gives us a minus sign. In this case, I get -1/3 -2/3. And this gives us -1. Now, for 2 qubits, it's not the same as for 1 qubit detecting superposition. For superposition, we got 0 if it's in superposition, and 1 or -1 if it's not. In this case, for an entangled state, this one, it gave us 1. For a state that is not entangled, it gave us 1. And for a state that is entangled also, it gives us -1. So it measures entanglement up to a point. What else can I say about this? Let me see. Oh, yes. Okay. Now, how do we apply this for the classification? Let's say I have a big circuit like this, and I apply a U gate, a circuit. So this is just a circuit, and I end up with the state psi. Now, again, this psi is just applying this U matrix. So the quantum circuit is a big matrix to the state with just zeros. And then I want to measure the expected value of psi on this C tensor to the number of qubits. This gets more and more complicated to do if you have more qubits. But one thing we know is that this is a value between -1 and 1. Now, what I'm going to do is I'm going to plot it here. So let's say I have -1 and I have 1. Then I want to put data into this circuit. So let's say I put this circuit depends on some data X. So that means we take the features of the data and we plug it into the circuit. and that prepares a state that depends on X. Now everything depends on X, 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 X. And then I measure it. Now, where is this value? Let's say it lies there, in this place. How can I use the expectation value to give a label to this data point? The way we do it is we look at the sign. So if it's positive, it corresponds to one class. If it's negative, it corresponds to the other class. And this is how we use it for classification. So we plug in another data sample, we obtain the final state, we compute the probabilities, then we compute the expected value, and we put it here. So now if it lies there, that means that the X corresponds to the, let's say, class 0. And if it lies in the other side, this corresponds to class 1. And that's how we use this expected value as a model. So as a thing that receives data and gives you a label. Now, let me go back to the paper. Now, as you can see here, there. So here they say a quantum model is a function like this. Now, this function depends on some theta, some x. What they're doing is they're applying this quantum circuit to the 0 state, and then they're measuring some observable. For us, this is always going to be the C operator. And then the other part is just the complex conjugate. And this is just the notation that we use for the expectation value with when we twist the cat for bra. That means we take the dagger. That means transpose conjugate. And now here you can see they say where 0 is some initial state of the quantum computer. That's because there are quantum computers in which the initial state is labeled as something else. Now they're just saying, so this is the initial state. For us, it's always the 0 state. This U of x theta is a quantum circuit that depends on the initial input x and possibly empty set of parameters theta. So this is a parameterized quantum circuit in which we put data and trainable parameters. Then M is some observable. Again, because there are quantum computers in which you can measure other observables, or you can do this thing where you rotate the qubit to measure along a different axis. And so that's this part. Are there any questions? Comments, complaints? So does that mean that everything is clear?
So X here is the, do you hear me well?
Yes.
Okay, sorry. So X here is like the input features.
Yes.
Like, okay. And then theta is just the hyperparameters of the model, basically, like the
Yes.
weights, for example, or something like that.
Yes. Okay. Is someone completely lost? Because it's not my intention to make you feel more confused.
So when you say like, I got, for example, why the I couldn't be used as an observable and why we chose Z, but like how important it is, how important could it be on the impact of the, like, how does it impact the results? How we choose M, the observable, like if we choose Z or some rotated version of it, or like how do, like in this paper, how did they decide what the M should be?
The answer is nobody knows.
So you just like try.
Yeah.
And see.
Yeah.
But my understanding is that you have the maximum contrast between two eigenvalues. with Z. You have the +1, -1, so you have the maximum contrast. It's one property that jumps to me.
Yeah, but if you measure another observable, what you do is you do like a rotation. So instead of measuring between -1 and 1, let's say you measure between -I and I, but you have always the same range for all the observables except the identity.
Yeah, because if you rotate Z, you probably you could get like something like 0.5 and -0.5. Basically, the eigenvalues are going, because you're using unitary operators. The domain of the eigenvalues is very limited. It's basically rotations.
Yes.
So you can rotate it, but you get maybe one eigenvalue at 0.5 and the other one at -0.5. So it's not a big improvement compared to the Z operator.
Yeah, in terms of the range, it's always the same range.
Yeah. So
unless you're measuring the identity.
It's some kind of contrasting function in the probability domain, because you're getting two states are +1, -1, and you taking the average over all the states.
Yes.
Yeah.
Does that answer the question?
Yes, thank you.
Okay. Okay, I'll try to move on with the paper. So again, this is how you define a quantum model. And what this means is this thing that I explained here, all of this. Then what do we do? Then we play around with the circuit, right? So again, this is everything you do. It's play around with the circuit, try different circuits, and see what happens. Now, what they're trying to do is what happens when you load the data into the circuit several times. And this is what they do in this equation right here. The W's, this is just a gate, so there. So we view the trainable circuit blocks as arbitrary unitary operations. So they ignore the theta that you can train it for now, and they just look at some unitary W. Now they plug this into the circuit. They call it W1, so you apply it once. Then you have SX. The SX is, okay, there. So the quantum circuit itself is constructed from L layers, each consisting of a data encoding circuit block SX. So this means you have a quantum circuit that depends on the data. So this is where you input the features of the data samples. In this case on the right, you can see now they're labeled L = 1. So this corresponds to one layer. They have the W, and then they have a place where they put the input data. And then they do it again. So the next one will be the second layer, and so on. Yeah, so the overall circuit looks like this. So you apply this L times, and they want to see what's the impact with respect to different amount of layers. And they use this Fourier series formalism to prove that the more times you encode the data gives you better performance. Let me see. Yeah, so again, this is just all the formalism. You don't need to understand these equations. Basically, what they're doing is they're trying to show that if you express the quantum state as a Fourier series, then you can keep track of the operations, and you can see that this will fit better the data that you're trying to fit. I think there's a figure that's more comprehensive than just all of these equations. Should be around here. Let me see. Single rotation polyencoding can only learn a sine function. Okay, I'll come back to this here. Okay, good. Now, here at the top, you have the quantum circuit. Actually, let me look at this. A parameterized quantum model is trained with data samples. So this is the white circles there. So these white circles, these are the samples you're trying to fit. And again, look at this. So these are values between -1 and 1. So this is an expectation value. So they're trying to train a generative model. That means that you have a time on the x-axis, and on the y-axis you have a range, and they put an expectation value there because that's what you measure on the quantum computer. You measure an expectation value of some observable. Since everything is unitary, this will be always between -1 and 1. And now they use these y dots as training data, and then to feed a target function. The target function, they give it as an expression in terms of Fourier series. Now with coefficients, they give you the coefficients they're trying to fit. The variation of the circuit is of the form, and they give you the form of the circuit. Again, look at this. So this sigma c is nothing more than the C operator. So they're measuring the C operator explicitly. This UX, this is the gate that depends on the input data, and that represents the circuit. Now the part on the left here is just the dagger of the part on the right. So 0 is a single qubit, and the circuit they're using is this circuit. So they apply a rotation along the x-axis where you input the data. So that means you rotate along the x-axis depending on the input feature that you put. So if the first feature is, I don't know, pi, then you apply a pi rotation over the x-axis. Now the W round blue symbols are implemented as general rotation gates parameterized by 3 learnable weights each. Each Rx is a single poly X rotation. Okay. Now this describes the circuit that you see here at the top of each figure. Now this dot corresponds, they said, square round blue symbol, which is the W. So the W is here, so you apply W, then the X. So the square blue symbol is a poly X rotation. So again, it's just rotation along the X axis. And then you apply a W again. So the W has the trainable parameters. Here, what they do is the left panel show the quantum model function and target functions, while the right panel show the mean square error between the data sample from G and F during a typical training run. Fitting in the input X as in the top row, the quantum model easily fits the target of degree 1. Okay. Okay, yeah. So this is the degree of the polynomial, right? So the data, it's depends on the degree of some polynomial. Just sampling from a polynomial function. Actually, yeah. So this should be like oscillations, and they try to mimic it like a polynomial function. In this case, you see that they fit exactly the data. Now, over the training, the MSE loss is the mean squared error. So that means you take the difference for each point, you square that, and you add all of the components, roughly speaking. The x-axis here is the training time. And this loss, what it's measuring is the distance between the blue dots, the predictions by the quantum model, and the white dots. So this is the data that you're trying to fit. Now, as you can see, this is very, very close at the end of the training. So that's why you see here in the training time, you can see that this loss goes closer and closer to 0. Now, if you change the degree of the polynomial, so this now you put 2x, now you cannot fit this thing. Now, what they do here is rescaling the inputs to 2x causes a frequency mismatch, and the model cannot learn the target anymore. Okay, so this is not the degree of the polynomial. Okay, I see. I see. So they just rescale the input data. So let's say if your values are between 0 and 1, what they do is now the inputs rescale to 0, between 0 and 2. This is just something that you do in actually in machine learning. What you try to do is you normalize the data. What that means is you subtract the mean, and then you divide by the standard deviation. So you have a data of mean 0 and 0 standard deviation. And this is the, again, something usual that people do in machine learning. What they're trying to do here is that compare with respect to the scale of the data. So if you scale to between 0 and 1, then you have the answer from the first sample, from the first figure. And if your data is rescaled between 0 and 2, then you don't fit completely the data. So the loss gets close to 0. But if you look at the fitting curve, it's not what you expect. Now, what else? Even with the correct scaling, the variational circuit cannot fit the target function of degree 2. Bottom row. The experiment in the paper were all performed using the Penny Lane software. Okay. Yeah. So in this case, they used the same circuit that's in the beginning, because they say, okay, look, this circuit is fitting this function correctly. So that means it's a good model. Maybe we can fit another function. So this is the G prime. Now the function is different. And they use exactly the same model. And they show that this model cannot fit this new data. What else do they have? Yes. Okay, this other figure is pretty nice. Now what they do is they move, let's see, what is this R? Okay, so they changed now. R means L. So R is the number of layers. Yes, is there a question?
Yeah, about the scaling of the input. So because they are using a rotation encoding, so like the gate Rx is applied. So X is, do they originally have to, like, well, X might be other values, and then should they standardize it between like minus pi and pi or something like that before input into that gate? Like, not sure if I understand how, like usually when you do classical machine learning, you would simply like try to standardize your input features between 0 and 1 or something like that, right? So
yeah,
how do you do it when you're treating it as rotation values?
yeah, that's the thing. So in principle, you don't know, but you can use some of the symmetry. So since you're looking at the rotations, then you can put it between minus pi and pi, or between 0 and 2 pi. Because it doesn't matter if you have like, for example, pi and then 3 pi, it's exactly the same rotation. So yeah, in principle, you do it, you rescale it between 0 and 2 pi. And what they do in this experiment, it's what you rescale is each one of the features. So even if the features are between 0 and 2 pi, and you rescale them, what you will do is you rescale between, let's say, 0 and 4 pi. Now, that doesn't mean that your data will be exactly the same. Only if you also, how do you call it, translate the data. So if you have your data between 0 and 2 pi, and then you move it to be between 2 pi and 4 pi, then it's exactly the same thing. But if you rescale it between 0 and 4 pi, then you have a different range from the data. Is that the...
I understand.
Okay.
Like
okay.
adding pi in. That would make sense. Yeah.
Yes. Okay.
Thank you.
Yes. Okay, so this is the other experiment. So again, it's a regression problem. Here you have the circuit. The dots means you have trainable parameters, and the X is where you input the data. And now what they do is they increase the number of times that you input the data into the circuit. So as you can see, basically R is the number of layers. So in this case, it's not good enough. If you do it 2 times, 3 times, it's better. It's getting better. If you do it 5 times, then you can fit almost perfectly the data. Now let's see what they say. Fitting a truncated Fourier series of degree 5 with some values using a quantum model that repeats the encoding 1, 3, and 5 times in sequence and in parallel. Okay, I see. So in sequence, okay, so that means you input the data on just one qubit, or you do it in several qubits. So as you can see here on the right, they input the data on the first qubit, then the second qubit, and the third qubit. But here they use the same qubit and they input the data on just the same qubit several times. This is called data re-uploading because you you take the data and you put it there several times.
It's the same
And
data
in
point
the
you're putting back. Is it the
sorry,
same data? Is it the same data point that you
yes,
are putting back? Okay.
yeah, it's the same data point. Okay, so and you have the same thing for 5. Then what do they say? Increasing R allows for closer and closer fits until R equals 5. Fits the data almost perfectly in both cases, illustrating that parallel and sequential repetitions of poly encodings extended the Fourier spectrum in the same manner. So extended the Fourier spectrum, what it means is that you can fit more complicated curves, roughly speaking. All models were trained with at most 200 steps of an atom optimizer. These are just details for the training. For the parallel simulations, W are not arbitrary unitaries, but implemented by smaller ansatz of 3 layers of parameterized rotation as well as entangling CNOTs. Yeah, so this is just giving you details on how the W was implemented, which is depicted by the hollow rounded gate symbols. Yeah, so these rounded hollow gate symbols, what it means is that you have an entanglement between the circuits in a way. The quantum models easily fitted the target function, which suggests that the results of this paper are of relevance for realistic quantum models. Spoiler alert, is not. Okay. Okay, so now I wanted to come back. There, okay. So this part 8, so they say a single polyrotation encoding can only learn a sine function. So what they show is that if you only use polyrotation, so that means polyrotations is either rotations along the x, the z, or the y axis. And then you can only fit a sine function. And apparently they prove it mathematically. The expressivity of the corresponding quantum model is fundamentally limited by the data encoding strategy. Yeah, again, so this depends how you put the data into the circuit. This is what tells you how the model is going to behave. So if you change the way you put the data into the model, this thing is going to change completely. So they're assuming that you input the data in either one of two ways. So like this, like by layers, and let's say in one qubit you put it several times, or in different qubits you put the data on all of the qubits at the same time. What is the next part? Repeated poly encoding linearly extended the frequency spectrum. Okay, so now what they say is instead of putting just some poly rotations, actually a single poly rotation, what they do is they repeat these poly rotations. And what they show is that it extends the expressibility of the model. What else?
So
Yes.
you have a sequence of points. If you look at the white circles, it's about 30 points. Because if you use a standard Fourier transform, you will transform the entire sequence of points and get your Fourier coefficients. But in that case here, how do they apply sequentially the points after points, or do they learn the parameters of the gates and they use those parameters for the next points sequentially? How do you process the entire sequence in that kind of circuit?
Yeah, I don't know. So they say they use a batch size of 25.
Okay.
So probably they do it randomly. So that means they take 25 randomly, and then they train for this specific 25, and then they take another 25 randomly, and then they proceed with the training. That's my guess. I'm not sure.
Okay,
But
so it's
yeah,
by
every time you
batch.
say, every time you say batch size, that's kind of the thing that you do.
Yeah.
You process the batch, and then the next batch, and then the next one.
Do we have some code that is available on Penny Lane? Or
Penny Lane, let me see. They usually put it at the top or at the end.
yeah.
Okay, so the end is filled with math. Oh, what is this? Partial Fourier series, yeah.
Oh yes, here.
Yes,
So,
GitHub.
okay, that's good. That could be
Yes.
interesting to check.
Yeah, I can put this, or probably
Yeah.
Tanya's already doing it. There. Yes. Let's see. Okay, they used Jupyter notebooks. That's good. Yeah, if you want, we can look at this next time.
Yeah.
We can
That'd
go
be
over
great.
this notebook. Okay. Now I have a homework for all of you. Look at the workshops that we did the first 3 weeks, where I explained all of this with the animations. So, or look at this one again, just so that you understand how they're using the expected value, what it means, and why do we use it. Okay. Is there any more questions, comments, complaints?
Maybe for Nicola, where can we find the previous workshops videos?
Yeah, the workshops, you can find them on the DOTS website, and I'll put the link also on the. I created, like at the beginning of the week, a web page on the Qatar website for this discussion group. So I'll put the link also of the videos of the workshops over there on this web page, and give you the link as well again.
Okay.
Okay. Anything else? Okay, if not, then you're free.
Right, thanks,
Merci,
Marco.
Marco.
Thank you, Marco.
You're welcome.
Thank you.
And I'll see you in 2 weeks. And
Yeah.
in the
Yep.
meantime, you get stuck with something, you can always write us an email to me or Tanya or both, and we'll answer you as soon as we can. Probably not more than a day. So
Thank you.
okay,
Merci.
All right, thanks.
see you next time.
See you.